Hello, this is Dr. Hanaa Assil and this is Unit 1 of October 2024 in the Pearson Edexcel International A-Level exams. Let's take a look at the questions and discuss the answers. So the first question here said, what is the molecular formula of naphthalene, of this compound? Of course, to get the molecular formula, you need to count all the number of carbons and the number of hydrogens. So write them out. Each carbon must have a total of 4 bonds. If you count the number of carbons and the number of hydrogens, it comes out C10H8. Magnesium azide is an ionic compound containing the azide ion, and we're told that the azide ion is N3-. The empirical formula of magnesium azide is what? How do we write the formula of anything? Magnesium is 2+, it has a valency of 2 or an oxidation number of 2. The azide, we're told, is N3-. That means when we write the formula, we can write the valency of one under the other. So magnesium, I need 2 azide ions, so it can be written like this. So the choice here would be the correct one. How many oxygen atoms are there in 0.01 mole of sulfuric acid? Remember that sulfuric acid, of course, we know, and it is written there, H2SO4. That means 1 mole of sulfuric acid has 4 moles of oxygen. So if I want the number of oxygen atoms, the number of moles is 4 times the number of moles of the sulfuric acid. And to get the number of atoms, how do we get number of atoms? The number of atoms is the number of moles times the Avogadro constant. So this is the answer. 2 identical sealed flasks containing different gases are side by side. Each flask contains 1 gas with the gases at the same temperature and pressure. Now we're told that flask A contains this number of moles of methane. Flask B contains this mass of a different gas. Which could be the gas in flask B? Well, first of all, the 2 gases are at the same temperature and pressure, so they would have the same number of moles. Flask A has this number of moles. That means flask B contains the same number of moles, and therefore from the mass and the number of moles I can get the molecular mass of the gas in flask B. Molecular mass is mass over number of moles. Remember, 160 milligrams is actually 0.16. You multiply by 10 to the minus 3 divided by the number of moles. This gives me an MR of 40. That means my gas has an MR of 40. Now, out of these choices, we have, first of all, argon, helium, neon. If you look at group 8, or the noble gases, the one that has an MR of 40 is actually argon. If we calculate the number of the MR of carbon dioxide, MR of carbon dioxide is 44, not 40. Diphosphane reacts spontaneously with oxygen, and we are required to balance. Now you should know how to balance. To balance, we count the number of atoms before and after the arrow and increase the one that is less. So if I look at this, I have 2 phosphorus before the arrow, 4 phosphorus after the arrow. That means I need to put a 2 in front of the P2H4, but that means I have 2 times 4 hydrogens, so I need 2 times 4 hydrogens after the arrow. Now I have how many oxygens total after the arrow? I have 10 plus 4, that's 14, so I need 2 times 7 before the arrow, and that is the balancing of the equation. Copper metal can displace silver from silver nitrate according to this equation. 10 grams of copper metal were added to an excess of silver nitrate. The silver metal was collected, washed with deionized water, left to dry. What is the mass of silver collected, assuming a 100% yield? So basically we're starting with 10 grams copper. How much silver? So we need to get number of moles of copper. So the number of moles of copper is mass over the molecular mass, 10 over the molecular mass of copper from the periodic table. This gives number of moles of copper. Now, we're asked about silver. We look at the equation and relate the number of moles. The equation says 1 mole of copper gives 2 moles of silver. That means number of moles of silver is twice the number of moles of copper. Now we have number of moles of silver. We're asked about the mass. How do we get mass? Mass is number of moles times mR, and that means we will get, according to the calculation, 34 grams. So the correct choice here would be between 20 and 40 grams. This question is about thermal decomposition of calcium nitrate, and we should be familiar with the fact that calcium nitrate, when it breaks up, it gives the oxide plus nitrogen dioxide gas plus oxygen. And the question is, what volume of gas is produced by the complete decomposition of 0.05 mole of calcium nitrate? So we're starting with 0.05 mole of calcium nitrate. Now, we want the volume of gases. Remember that we have the gases formed are nitrogen dioxide and oxygen. So if I'm starting with 0.05, according to the mole ratios in the equation, 2 moles of calcium nitrate give 4 moles of NO2. That means NO2 is twice the number of moles of calcium nitrate, and 1 mole of oxygen. So the number of moles of oxygen is half the number of moles of calcium nitrate. Now we want the total volume. That means we can use the total number of moles of the gas. Total number of moles would be the 0.1 plus the 0.025, so that's 0.125. And we know that at room temperature and pressure, the volume is number of moles times 24, that is 3 decimeter cubed. Ethanol is formed from glucose during fermentation. What is the atom economy for formation of ethanol? How do we get atom economy? Atom economy is the MR of the required product over the MRs of all the products times 100. And please remember, when you're calculating atom economy, you take into account the coefficients. So atom economy is the MR of ethanol. MR of ethanol is 46. We have 2 of them, so the atom economy is 2 times the MR of ethanol over the total MRs of the product. So that's 2 times the MR of ethanol plus 2 times the MR of CO2 times 100. This gives the percent atom economy. The table shows some data about fundamental particles in an atom. An atom of hydrogen can be represented as H with a mass number of 1. What is the mass of this hydrogen atom? Now remember that the hydrogen atom has what? It has 1 proton and 1 electron. So the mass given in the table of the proton plus the mass of the electron, that would be the total mass of the hydrogen atom. Which of the particles would be deflected by an electric field? Remember, which of these particles is charged? You know that an electron has a charge of -1, a proton has a charge of +1, a neutron has no charge, it is neutral, so only electrons and protons are deflected when passing through an electric field. This question is about period 3 elements. Which statement is not correct for these period 3 elements? Please pay attention. Is the question asking for which one is correct or which one is not correct? So we're looking for which one is not correct. Okay, the first choice says atoms of chlorine have the highest first ionization energy. Well, if I look at the periodic table, I find that these elements are, as we are told, period 3, going from left to right in any period. You should know that the atomic radius decreases, and we said that is because same number of shells but increasing positive charge in the nucleus. So the atomic radius decreases. That means the outer electron is more strongly attracted to the positive nucleus, therefore more energy needed, so the ionization energy increases going from left to right. So that first statement is correct. Now the second statement says ions of chloride and sulfide have the same ionic radius. Well, let's look at this. Sulfur has 16 protons attracting a total of 18 electrons, while chloride has 17 protons attracting the same number of electrons, and we said more positive charge means more attraction to the nucleus, and therefore the atomic radius gets smaller as the protons increase, or smaller number of protons, weaker attraction to the nucleus, so larger radius. So actually they don't have the same ionic radius. The one that has more protons, smaller radius. Now, what are the other choices? When you are answering, please check that the other choices are not the correct choice. So C says atoms of sodium have the largest atomic radius. Well, yes, we said the atomic radius decreases going from left to right, so sodium has the largest atomic radius of that period. Atoms of phosphorus have the most unpaired electrons. Well, if we sit down and do the electronic configuration of phosphorus, phosphorus is 15, so 1s2, 2s2, 2p6, 3s2, 3p, 3p3. So it does have a high number, 3 unpaired electrons, at least in the outermost shell. So actually that is a correct statement. Melting temperatures of these elements are shown. Which of the elements has the strongest intermolecular forces? Remember, intermolecular forces means between the molecules, not inside the structure. So if we're looking at sodium, magnesium, aluminium, we know that these are metals with increasing number of delocalized electrons. So stronger attraction between the positive ions and the negative electrons. So the melting temperature of metals group 1, group 2, group 3 are increasing. Now silicon is in group 4. It has the highest melting temperature in that period because giant 3-dimensional structure with strong covalent bonds inside the structures that need to be broken. So all of these do not have intermolecular. They have strong covalent bonds in the case of silicon, or strong attraction forces between positive ions and negative electrons in the case of metals. Now, the non-metals, phosphorus, sulfur, chlorine, are the ones that have intermolecular structures, intermolecular forces, because they have molecular structures. Now, which one would have the strongest? The bigger molecule. So, of course, you should remember that phosphorus is actually a molecule made up of 4 atoms. Sulfur is a molecule made up of 8 atoms. So that is the one that would be bigger, more electrons, so stronger intermolecular forces. Which row of the table shows properties consistent with the type of bonding? Okay, so if we're looking at ionic bond, let's look at ionic bond. Are ionic compounds soluble in water? Yes. Melting temperatures, we said they are high. Electrical conductivity of a solid, ionic compounds do not conduct electricity as a solid, so actually A is correct. If we look at the metals, metals, of course, are not soluble. They do have high melting temperatures, but their electrical conductivity as a solid is good. So C and D are not correct. The metal is insoluble, so we should be choosing D, but then D says electrical conductivity of the solid is poor, and that's wrong. So actually our correct answer is A. Ionic compounds are soluble in water, have high melting temperatures, remember strong attraction forces between positive and negative ions, and as a solid they do not. Then this question says, which ion is isoelectronic with a noble gas atom, something in group 0 or group 8? So, which of these would have the electronic configuration of a noble gas? Well, let's see. H plus is something that doesn't have any electrons at all. O minus oxygen originally has 8 electrons. If it is O minus, that means it has 1 extra electron, so that's 9. So that's 1s2, 2s2, 2p5. So it's not really a noble gas configuration. What about scandium 3+? Well, scandium alone has 21 electrons. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. Remember, when we fill electrons, we fill the 4s first before the 3d. But then we want scandium 3+. When we remove electrons, we start by removing the electrons in the 4s also, because that is the outer shell electrons. So we need to remove 3 electrons to have a 3+. So we're going to remove the 2 electrons in the 4s, the 1 electron in the 3d. So we're left with 1s2, 2s2, 2p6, 3s2, 3p6. That's 18. 18 is the electron configuration of argon. What about zinc? Let's check zinc. Zinc is 30. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. What if I want zinc 2+? Well, zinc 2+ will just remove the 2 electrons in the 4s. I'm still left with a 3d10, which is not an electron configuration of a group 0. Cycloalkanes undergo free radical substitution reactions by the same mechanism as methane. 3 isomeric cycloalkanes are shown. Which of these react with chlorine to produce 4 different monochlorinated products? That means we want to react with chlorine and put chlorine in 4 different positions or on 4 different carbons. So let's take a look. Isomer X has how many different CHs that we can replace the hydrogen with a chlorine? Well, this would give 4 different monochlorinated products. What about Y? Y has only 2 different CHs that can be replaced with chlorine. Isomer Z has 4 carbons in which the hydrogen can be replaced by a chlorine, so it is X and Z. Then this next question says polymerization of alkenes occurs via a free radical mechanism. This reaction is started by the addition of small amounts of another compound. The structure of one of these compounds is shown. This can be represented by ROOR, where the R is that part with the benzene ring, double bond O, and a bond. Now, which step in the mechanism is an initiation step? Now, if you remember when we talked about free radical mechanism of alkanes, halogenation of alkanes, what was the initiation step? The initiation step was the first step in which the bond between the 2 Cls is broken down by homolytic fission. Homolytic fission, we said, means 1 electron from the bond goes to each atom to form 2 free radicals. So out of these choices, which one is the initiation step? Well, it's the one where the bond breaks to form 2 free radicals. This question is about cyclohexene, a cyclic alkene. What is the general formula of cyclic alkenes such as cyclohexene? Well, let's see. If we look at this compound, we look at the carbons and the hydrogens. This is something that has C6H10. So if I were to write a general formula, remember how to write a general formula? We said to write a general formula, it is CnH something. So if I say N is 6, what is H in this case? This would be twice minus 2. So 2 times 6 is 12, minus 2 is 10, so it is CnH2n minus 2. Cyclohexene can form an addition polymer, which diagram shows 2 repeat units of this polymer. Remember, if I have that with a double bond, an addition polymer means I'm going to add another unit to each of these carbons. So we have this double bond, we can remove it, make it into a single bond, and a bond on the right, a bond on the left, and I join that to another unit. So this looks like which of these? So obviously it looks like the choice in D. Cyclohexanol can be converted into cyclohexene. So we can change it to remove H and OH, dehydration, and form a double bond. What mass of cyclohexanol is needed to make 7.2 grams of cyclohexene if the yield is 72%? Well, we are starting with a certain amount of cyclohexanol. I want to make 7.2 grams, but that is a yield of 72%. So that means if the 7.2 is a yield of 72%, what was it supposed to be for 100% yield? So it was supposed to be 10 grams. So I was supposed to get 10 grams of cyclohexene. So what is the mass of cyclohexanol I started with? Well, let's get the number of moles of the cyclohexene. So that is 10 over the MR of the cyclohexene. So the cyclohexene is 0.122 mole. The cyclohexanol would be the same. It's a 1-to-1 ratio from the equation. Then I can get the mass. The mass is number of moles times the MR of the cyclohexanol. So I should start with 12.2 grams. The molecule shown has 2 double bonds, which is the correct identification for each double bond. Remember, when we have double bonds, we said we have restricted rotation around the double bond. So you cannot turn the carbons around due to restricted rotation of the double bonds. When there are two different groups attached to each carbon, if the ones with higher MR are on the same side, that is a Z isomer. If the ones with the higher MR are on opposite sides of the double bond, that's an E or a trans. So let's take a look at each double bond. Now that double bond number 1, it has the substituents with the higher MR on opposite sides of the double bond, so that's an E. Now, what about double bond number 2? Well, again, the substituents with the higher MR are on opposite sides of the double bond, so that again is an E. Sodium hydroxide can be obtained as a hydrate. When heated, the water of crystallization is lost, leaving anhydrous sodium hydroxide. An experiment was carried out to determine the value of X in the hydrated salt. Weigh and record the mass of a clean, dry crucible. Add approximately 1 gram of sodium hydroxide X water to the crucible and record the mass. Heat the crucible and its contents until a constant mass has been reached. Remember, this is how we get rid of the water and determine how much water we had. Now, after allowing to cool, reweigh the crucible and the anhydrous solid, and we should continue that until a constant mass has been reached. Calculate and record the mass of the anhydrous solid. Repeat these steps using different masses of hydrated sodium hydroxide. So these are the results. They did it with different masses of sodium hydroxide X water and determine the mass of the final solid. Complete the graph by plotting the points, labeling the axes, including a straight line of best fit. So remember, what goes on the x-axis is the independent variable, which is the mass of the hydrated salt that we're weighing. Please do not forget to include units. What's on the y-axis is what we're measuring at the end, so that's the mass, and we plot with small x's, join with a line of best fit. Use your graph to determine the mass of the hydrated salt needed to form 4 grams of sodium hydroxide. So this is the graph we drew. We want 4 grams of sodium hydroxide. Move horizontally to the line and go down to find the mass of the hydrated salt that we started with. So from the graph, it is 5.8. Calculate the value of X using your answer and the equation. So what do we have? We had 4 grams of sodium hydroxide. So I can get the number of moles. The MR of sodium hydroxide is 40, so the number of moles mass over MR is 0.1. Now, from that equation, the number of moles of sodium hydroxide is the same as the number of moles of the hydrated salt. That means I can use that, and we have the mass from the graph is 5.8, and the number of moles, I can use that to get the MR. MR is mass over number of moles. And that means the total MR of the hydrated salt is 58. So the mass of sodium, the MR of sodium, oxygen, hydrogen, 18. X, the total is 58. I can solve for X. So according to this, X is 1. Sodium hydroxide also forms a heptahydrate, so 7 water. The X here is 7. Calculate the mass of this heptahydrate needed to make 250 centimeter cubed of a solution of sodium hydroxide of concentration 0.15. So we have the number of moles that we need is concentration times the volume. Of course, the volume, please do not forget to divide by 1000. So this is the number of moles. he wants mass, so I can use the MR of the hydrated salt. The MR comes out to 166, and the mass would be number of moles times MR, so that means I need 6.2 grams. Molecules of isooctane found in petrol have 8 carbon atoms. The skeletal formula is shown. Give the molecular formula, empirical formula, and IUPAC name for this compound. So, first of all, how do we get molecular formula? That's just the total number of carbons, total number of hydrogens. So, we find that this is C8H18. What is the empirical formula? It's the formula showing the simplest ratio. So, can I simplify 8 and 18? Divide by 2. The empirical formula is C4H9. Now, what is the IUPAC name of this? We said to name the compound, we look at the longest chain. So, this is a chain of 5 carbons with only single bonds between the carbons. So, this is actually pentane. And then we have methyl groups as substituents. We have 2 on carbon number 2 and 1 on carbon number 4. Of course, we start counting from the side that gives the lower number. So this is 2, 2, 4. You have to give a number for each substituent. I have 3 methyl, so that is a trimethyl pentane. Isooctane and octane are isomers that are both found in crude oil. Octane has a boiling temperature of 125 degrees Celsius. Isooctane has a boiling temperature of 99. So these are a mixture of liquids with different boiling points. This difference in boiling temperature is used to separate the two isomers. The technique is the same as that used to separate crude oil. So what is the technique used to separate a mixture of liquids that have different boiling points? Of course, that is fractional distillation. Describe how this technique, fractional distillation, separates the two liquids. So remember that in fractional distillation, what we do is the mixture is heated in a flask connected to a fractionating column and a condenser. Now, the one with the lower boiling point will boil off first. So isooctane, we were given the boiling point, so the isooctane has lower boiling point. That means it will boil, be cooled and condensed in the condenser first to be collected as a separate fraction. Remember, so long as we're collecting one of the fractions, the thermometer remains at a constant temperature. And then as soon as all the isooctane has been collected, then the temperature will start to rise until we reach the boiling point of the next fraction and so on. Isooctane is added to petrol to increase its what we call octane rating. Some high-performance engines need fuel with a higher octane rating. Write the equation for the complete combustion of isooctane. Okay, isooctane we already got was C8H18. Complete combustion means we're reacting it with oxygen to give carbon dioxide plus water. And then we need to balance. Remember, we count the atoms before and after the arrow and increase the one that is less. So here before the arrow I have 8 carbons. I need 8 carbons after the arrow. I have 18 hydrogens before the arrow. So I need 2 times 9 hydrogens after the arrow. Now how many oxygens total after the arrow? I have 2 times 8, 16, plus 9, 25. So that is 2 times 12.5. Carbon monoxide and nitrogen monoxide are both pollutants produced in car engines. Describe how each pollutant is formed in car engines, including the conditions required. So, remember, how do we get carbon monoxide? Carbon monoxide is produced by incomplete combustion of fuel. And this happens when there is lack of oxygen or a limited amount of oxygen. What about oxides of nitrogen? Remember, oxides of nitrogen are formed due to reaction of nitrogen and oxygen in the air around the engine. It's not from the combustion of fuel. It's from the air around the engine when there is high temperature or the spark due to ignition. This causes nitrogen and oxygen in the air around the engine to react, and this is how we get oxides of nitrogen. Identify another pollutant other than carbon dioxide, carbon monoxide, and nitrogen monoxide. In car engines, well, the other pollutant is sulfur dioxide, and this comes from combustion of fuel because the fuel contains sulfur impurities. Isooctane reacts with an excess of chlorine to form a mixture of chlorinated compounds containing the same number of carbon atoms as isooctane. State the type and mechanism of this reaction. Now, this is an alkane reacting with chlorine. Remember, alkanes react with chlorines in free radical substitution reactions. What is the essential condition for this? Remember, free radical substitution reactions of alkanes require UV light or ultraviolet radiation. One of the chlorinated compounds contains this percent carbon, this percent hydrogen. Remember, we're talking about chlorinated, monochlorinated compound. So we have carbon and hydrogen and chlorine, and we have the percentage of carbon, percentage of hydrogen, so the rest of 100 is the percent of chlorine. We divide first, we're getting empirical formula, so we divide by mass number and then by the smallest, and this gives this ratio. When the ratio comes out as a fraction like this, 2.66, please do not round it up. Don't say it's 3 and don't round it down. Don't say it's 2. We multiply through by a number that will change this 2.66 into a whole number. So you'll find that if you multiply by 3 all through, then the ratios are 8 to 15 to 3. So the formula is C8H15Cl3. This question is about reactions of propene. So we have propene plus HCl or propene plus water. Remember, alkenes can react with HCl or water to add these compounds. The double bond opens up and we add an H and a Cl or an H and an OH to the carbons. Now, what is the mechanism and type of reaction of these? Remember, all alkenes do electrophilic addition. The double bond opens up and substituents are added on the carbons. Explain why the structures of the intermediates in reaction 1 mean that 2-chloropropane is formed in greater yield than 1-chloropropane. What happens is we have propene reacting with HCl. Remember that what happens is the double bond attacks the hydrogen, which is slightly positive, and the electrons go to the Cl, which is slightly negative. Now this means I add the hydrogen to one of the carbons of the double bond, and the other carbon becomes a positively charged carbon, which we call a carbocation. So if the hydrogen is added to the carbon on the right, then the carbon in the middle becomes the positively charged carbocation, and that's a secondary carbocation. But if I add the hydrogen to the carbon in the middle, then the carbon on the end is the positively charged carbon. That's a primary carbocation. And we find that if the 2-chloro is the main substituent, that is because it was formed from secondary carbocation, and secondary carbocation is more stable than a primary carbocation, and this is because the positively charged carbons has methyl groups around it, and the methyl groups are electron donating, or we say they have an inductive effect. So usually the hydrogen, when we do this kind of reaction, the hydrogen is added to the carbon on the end, and the Cl or whatever we're adding goes to the carbocation in the middle, because that is usually a secondary or a tertiary, which is more stable than a primary carbocation. Reaction 2 proceeds in 2 stages. So remember, reaction 2 was adding water to the double bond, but this is usually in presence of an acid like sulfuric acid, which acts as a catalyst. So what happens is the double bond reacts with the acid first, and then this can go on to react with the water. So complete the mechanism by including the intermediate structure, curly arrows, relevant dipoles, charges, and lone pairs. So we're adding this compound to a double bond. This is electrophilic addition, and that means the double bond attacks the slightly positive end of the other carbon, of the other molecule. So here I have a slightly positive hydrogen and slightly negative oxygen. The double bond attacks the hydrogen, and the electrons between the H and the O go to the slightly negative oxygen. So I end up with a carbocation. In this case, it's a secondary carbocation, and I have that structure in which the oxygen has a lone pair of electrons and a negative charge. Don't forget the negative charge. It's now a full negative charge, and the lone pair of electrons on the oxygen attack the carbocation and is attached to that carbon. Periods in the periodic table show trends in physical properties. Explain the general trend in the first ionization energies for period 2. So if we're talking about first ionization energies, what is the general trend? First of all, you will find that as in general, the first ionization energy increases from left to right. Now, why is that? Remember that from left to right in a period, the radius is decreasing. This is the same period, that means the same number of shells attracted to positive protons in the nucleus, but as I go from left to right, the number of positive protons increases. So the atomic radius decreases from left to right, and that means the valence electrons or outermost electrons are more strongly attracted to the nucleus, and higher energy is needed to remove them. Now explain which one of the elements from lithium to nitrogen deviates from this general trend. We said as I go from lithium to nitrogen, it's generally increasing, but where is it not increasing? From beryllium to boron. Now, why is it not increasing from beryllium to boron? You need to look at the electron configuration of each. So, beryllium is 1s2 to s2. That means I have paired electrons in the 2s. Now, boron is 1s2 to s2 to p1. So the electron we're removing is in the 2p, which is higher energy than the 2s. So the electron in the 2p is more easily removed, less attraction to the positive nucleus, so lower ionization energy. Identify the period 3 element that has the following successive ionization energies. Remember, from the successive ionization energies, I can determine in which group is it. So remember, we go from first, second, third, fourth. Where do we have a big jump in the ionization energy, a big increase? So we're going from 8,000 to 27,000. That means this is something in group 6. So we're looking for something in group 6, period 3, group 6, period 3 is sulfur. The diagram shows the melting temperatures of the elements in period 2 from lithium to nitrogen. Complete the diagram by putting crosses to show approximate melting temperatures for boron and nitrogen. So we're looking at period 2, that means lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. We're going from lithium, beryllium, boron. We said these are metals with increasing number of delocalized electrons, and we said as the number of delocalized electrons increases, the attraction forces between the positive ions and the electrons increases, and therefore the temperature increases. So we should have an increase in temperature from lithium to beryllium to boron. Then carbon has a giant 3-dimensional structure. That means we have strong covalent bonds, and that means higher melting temperatures. So carbon should be high. It should be higher than beryllium, and beryllium higher than boron, and boron higher than beryllium. And then we go into nitrogen, oxygen, fluorine. All of these are simple molecular structures with very low boiling points or melting points. So where are we going to put? We're going to put the giant structures, lithium, beryllium, boron. So boron is in between beryllium and carbon. Now, where is nitrogen? We said nitrogen is a simple molecular structure with very low melting temperature, lower than lithium, so it's very low down there. Explain why the melting temperature of carbon is high with reference to its structure and bonding. We know that carbon can either be diamond or graphite. Now, why is it very high? And actually group 4 is the highest melting temperature in the period. Why? Because it has giant 3-dimensional structure with many strong covalent bonds that need a lot of energy to be broken. Boron, aluminium, and thallium are in group 3 of the periodic table. These elements form molecular compounds with chlorine with the formula BCl3, aluminium trichloride, thallium trichloride. The shape of these molecules depends on the electronic structures of group 3 elements. So first of all, what is the electronic configuration of aluminium? You should know from the periodic table, aluminium has an atomic number of 13. How do we distribute it? 1s2, 2s2, 2p6, 3s2, 3p1. Compare and contrast the electronic structures of boron, aluminium, and thallium. Well, if we look at them, they're all in the same group. So we know that all the elements in the same group have the same what? They have the same number of electrons in outer shell, so they all end in p1, but the difference between them is they will have different number of shells. Remember, compare and contrast means we say they are similar in what and different in what. Deduce using electron pair repulsion theory the expected shape of each of these. Well, we know that in order to draw the shapes, we should take into account the number of bonding pairs of electrons, the number of bonds, and if we have any extra lone pair of electrons in the central atom. So boron is in group 3 and it has only 3 electrons in its outer shell, so it's going to make 3 covalent bonds. We need to put them as far away as possible from each other for minimum repulsion. So boron with 3 bonding pairs of electrons and no lone pair of electrons on the central atom, this is a trigonal planar structure with a bond angle of 120. Aluminium chloride is the same and thallium chloride is the same. So we have you have to explain 3 bonding pairs of electrons, no lone pairs of electrons on the central atom. So all of this is trigonal, planar for minimum repulsion between the 3 bonding pairs of electrons. Aluminium chloride is a solid at room temperature. At relatively low temperature, it sublimes. A sample of 5 grams of aluminium chloride was heated at this pressure, this temperature. When all aluminium chloride had vaporized, the final volume is this. Show that the data is consistent with the formula of aluminium chloride as being Al2Cl6. Now, in order to show that it is Al2Cl6, that means I should get the correct MR. So, using the ideal gas law, PV is equal to nRT, I can use that to get the number of moles and then determine the MR, or just put it directly into the equation. Number of moles is mass over molecular mass, and that means the molecular mass is mass times R times T over PV. Now, what is the mass? 5 grams. R, 8.31. Temperature, we put the temperature in Kelvin. Over pressure, the pressure should be in Pascal, so that is okay. Times the volume. Now, the volume has to be in meter cubed. So, we have it in centimeter cubed. We multiply by 10 to the minus 6. This gives an MR of 267.4. Well, if you calculate the MR of Al2Cl6, it is 267, so that is correct. Draw the dot and cross for Al2Cl6. Remember, we said aluminium chloride dimerizes because it can form dative bonds. So, chlorine of one molecule forms a dative bond with the aluminium of the other molecule. Remember that aluminium has only a total of 6 electrons around it, so it can take 2 more to form 8. So each aluminium takes 2 electrons from the neighboring chlorine to form dative bonds. Okay. Last part, thallium also forms ions containing chlorine. For example, the thallium Cl4 3- ion. In this ion, the thallium atom has 10 electrons in its outermost shell. Phosphorus in phosphorus pentachloride also has 10 electrons in its outer shell. So draw the shape of the thallium with 4 chloride ions and predict the bond angles. Include any lone pair of electrons that influence the shape. Remember that we're going to draw it just as we draw phosphorus pentachloride, but phosphorus has 5 chlorines, thallium has 4 chlorines and a lone pair of electrons. Now we're going to predict the bond angles. Remember that the chlorine on top or below makes an angle of 90 with the plane of the thallium, and the chlorines on the plane of the thallium are forming a trigonal planar structure, which forms a trigonal bipyramid in which the bond angles are 120 and 90. This is the end of the paper. I hope this was useful and good luck on your exams. Thank you for listening.